Hey everyone, in this section we're going to be looking at three main topic areas, the first of which would be examining some different important features of functions that are going to be important for us to understand, mainly looking at that through the avenue of the graphs of these functions to understand those characteristics. And then the second thing that we'll do is we'll look at ways that we can kind of model some real world relationships a little bit and look at some characteristics associated with that. And then the last thing that we'll do at the tail end here is be able to write equations and evaluate and understand the graphs of piecewise functions. So we want to first of all begin by examining increasing and decreasing intervals of functions. So if you take a look at this graph that you're seeing right here, I'm going to highlight in the color green this portion of the graph. That part of the graph would be an increasing portion of the graph. Now what we want to try to do here is we want to specify an interval upon which this function is increasing, and when we do so, we need to give an interval of the domain of this function. So in other words, the inputs or the x's. So basically, like from this x coordinate to this x coordinate, so this interval of the x-axis, okay, that's the portion of the domain of the function on which this is increasing. So what we're going to want to say, and we'll look at some examples in a little bit, is that this function is increasing on the interval from whatever that left coordinate is to the right coordinate. So if this is, like a and b, then it increases on that interval a to b. So I used interval notation right there. And then I also did use parentheses around the a and the b, because at the endpoints of that interval, it's not really actually increasing at the endpoints in particular, so we're going to like exclude that. And so, yeah, just using an open interval like that is perfect for identifying an increasing interval like that. Let me give a succinct definition for what it means for a function to be increasing on a particular interval. So if we know the following, if we know that we plug in some number c into a function f, and we find that that function value is less than plugging in some other number d into that function, for every possible choices of c and d within this interval a to b, where we also know that c is less than d, then we can say that f increases on that entire interval from a to b. Okay? All right, that's a very abstract, mathematical sort of definition. So let me bring that back to the graph that you're seeing right here so you can sort of see like a pictorial representation of what's happening here, right? So basically all I said is that we could pick any two numbers c and d on an interval from a to b. So like I even call this interval a to b, right? So let's say I picked like this right here to be c and then this right here to be d, and I could have picked any other coordinates, right? Now we know that c is less than d, right? Based on my choices of c and d. Now, if I find f of c and I find f of d, the spot on the function corresponding to c is right here. So this is going to be like where f of c is, right? And then the spot on the graph where d is like right here. So that means that f of d is right there. And you can see that, right, for c being less than d, we also have that f of c is less than f of d, okay? And that's actually going to hold for all possible choices of coordinates I could have picked between a and b, okay? And so because of that, then we know that this function is going to be increasing on that entire interval from a to b, okay? So for a decreasing interval definition, it's basically sort of the same thing, but we would just say that if we find that f of c is greater than f of d, for every c and d that we could choose in a to b, where also c still needs to be less than d, okay, then we would say that f decreases on the interval from a to b, okay? So basically, all you need to do to identify a decreasing interval on a function is if you follow the graph from the left to the right, it should be going downhill, right? So this little interval right there would be a decreasing interval. Now, when you're going to specify an interval like that, you will definitely want to specify it in terms of the, x numbers that you're seeing there. And then anytime that a function is just going like flat like this, we would consider that a constant interval because the output values are all staying constant. So what you'll see happen right there is for every c that is less than d, that actually f of c and f of d are actually going to be equal, right? When c and d are different numbers from each other. So that, of course, would hold for constant intervals. So now let's take a look at a few examples here where we are asked at the top right here to identify the increasing and decreasing and constant intervals of the graph of each function, right? So I'll zoom into this very first example right here. You'll notice that right here, this interval would be a constant interval of the function. So when we give that, we want to specify the interval of the domain. right? And so it goes on forever towards like negative infinity. So we can say that this function is going to be constant on the interval going from negative infinity all the way until we get up to that x number right there at -1, right? And then a parenthesis would probably be the most appropriate thing to say that it's constant right there. You might be able to make an argument for putting a bracket on the -1, but parenthesis is just fine. And then there are a couple of places, so right here, and then also right here, two different intervals where the function is going downhill from left to right, so where it's decreasing. So we would be able to say that it's going to be decreasing on this interval right here. That goes between -1 and 1 on the x-axis. So on -1 and 1, like that. And then also this interval right here. And then because of the arrow of that piece right there. It's going to go on forever and ever and ever and ever. So when it starts at 4, it's actually going to go on until infinity and decrease, right? So if you like wanted to say just like on -1 and 1 and like the word and for infinity, it's increasing right there, or not increasing, decreasing, right? But sometimes we can actually join those two sets together if we want and use a union symbol to unite them and say that it's just decreasing on this union of the two sets, and that'd be a fine way to do that too. Okay. And then of course, as you can see, there's just this little part right here that's going uphill from left to right. So you'd be able to specify that interval in which it's increasing, which is going really between 1 and 4 on the domain of that function. Okay, good, good, good. Okay, so when you take a look at this function right here, I'm just going to go ahead and color everything right now, just in terms of where it's increasing at, and then also where it's decreasing at, right? Okay, so there you can see those increasing and decreasing intervals. So like right here, almost like the entire negative part of the x-axis is where this function is increasing. It's just at -4 itself. There's no function value right there. So we would just basically need to split it up into two separate intervals, one from -infinity until -4, and then the other from -4 until you get to 0. And then, of course, you can unite them together, and then that would be a portion where this graph, of course, is increasing. And then where it's decreasing is pretty much just symmetrical because it has that asymptote at +4. So from 0 to 4, and then from 4 to infinity are those two different places where this function is decreasing. And then if you just unite them together, then of course those are going to be the decreasing intervals of that particular function. And then one last example of looking at increasing and decreasing portions of functions. You can see there's this graph right here where obviously it's decreasing right here. And then it's just asymptotically approaching the x-axis. And so it never flattens out right there. It's always going to be like going downhill. So the entire like function is decreasing, right? And it seems to be coming all the way from over here at -infinity. And the graph is going to keep pushing to the right forever and never straighten down to go vertically. It always keeps pushing to the right. So that means that this function is always decreasing, right? So the probably best way we could say that is just decreasing on R, or the entire real number line, the entire x-axis. If you wanted to use interval notation and say -infinity to infinity, that would of course totally be fine too. Next, we want to take a look at what it means for a function to be positive or negative on an interval. So I'm going to start by just defining what that means first of all right here. So what we can say is that if f of x is greater than 0 for all x within a particular open interval from a to b, then we can say that f is positive on the interval from a to b. Okay? So ultimately what this statement right here says is just that the y values need to be greater than 0, right? For all x within a particular interval, and then it's going to be positive. So just very simply placed right here, this interval right here of the function is where it's positive because all the y values are positive. So it's just simply above the x-axis. So you just have to be careful because right here at that point and that point right there, it's not positive, and neither is it negative right there. So we want to exclude those particular points. So, you know, if this number was right here A and this number right here was B, we would just say that the function is positive, so f of x is positive on the interval from A to B with parentheses, right? And then this part of the graph and this part of the graph that's below the x-axis, of course, where it's going to be negative, right? So you have pretty much a similar definition, just if f of x is going to be less than 0 for all possible x that are within a particular interval from A to B, then we can say that f is negative entirely on that interval from A to B. Right. So we're going to actually look at the same graphs that we looked at in terms of increasing and decreasing and constant intervals here. So in this first example graph right here, for us to identify where it's going to be positive, just look at all the places where it's going to be um, above the x-axis, right? So this, and all the way until you get to like 6 right there, right? That's where this graph is all positive. So we have to specify the interval of the domain. So everything from negative infinity until you get to like -1, right? Now we can actually include -1 because of that filled in dot right there, okay? And then everything right here. So the graph is actually all continuous. So literally this whole entire interval from negative infinity to 6 is where the function is going to be positive, right? So that's a positive interval of the graph. And then this part right here that's below the x-axis would start at 6, so parenthesis 6, and then it's going to go to infinity because of the arrow. That part of the graph would be a negative part of the graph, right? And then for the other graph that you see right next door right here, these couple parts right here are where the graph is going to be positive. So this interval right here goes from negative infinity until you get to -4. So negative infinity until you get to -4, it's positive there. And then this interval goes from 4 to infinity. And then if you wanted to put a union symbol, that'd be great. And that tells you where the function is going to be positive at. And then this whole continuous little chunk right here, which is squeezed between -4 and 4 right there, that interval is going to be a negative interval of the function, of course, right? And then the last graph right here, actually, because it asymptotically approaches the x-axis as x goes towards negative infinity, the graph is just entirely below the x-axis, right? So it's just going to be negative on r on that particular interval of the x-axis, or just on negative infinity to infinity. Next, we want to take a look at what we call relative extrema of a graph of a function. So ultimately, extrema, this is just the plural version of the word, and then this right here is the singular, if you're just talking about one single extremum. They're just the high and low points in a graph, so ultimately maximum points and minimum points, right? So they're really just, yeah, max and minimum points. Okay. So one thing that's really important to understand about maximum and minimum points is that they are always going to occur. They occur only at turning points of the graph of a function. Okay. So we need to define what it means for us to have a turning point. So right next door, of course, is where we want to define what a turning point is. So ultimately what a turning point is it just needs to be a point where the function is going to change, and one of two things could happen. It needs to change either number one from increasing to decreasing at that point, or number two, it needs to change from decreasing to increasing at that particular point. So in this very graph that I'm zooming into right here, there are a couple of turning points because the function increases right there and then it hits that little point right there where then on the other side of the point it changes to decreasing. So we would call that particular point a turning point, right? And that would actually be considered like a maximum point because it's a little high point in that local area of the graph. And then it increases on the other side of this other point down there where there's that little lower point. So we'd also call that a turning point because it changes from decreasing to increasing right there. We would more commonly probably call that a minimum sort of point, right? And there's just one thing to keep in mind right here is like you see this little point right here where okay it's increasing, but then on the other side of the point it keeps increasing. So that particular point that you're seeing right there is not a turning point of the graph of the function because the turning point needs to change from increasing to decreasing or vice versa, right? So yeah, minimum and maximum points are only going to occur at turning points of graphs, right? So here we're asked to identify the relative and absolute extrema of the graph of the function. So I haven't yet defined what it means to be a relative versus an absolute extrema of the graph of the function. I'll get there in just a little bit. So for right now, we should just be able to at least identify like, okay, so right here, there's a high point of the graph. Here's a low point of the graph. Like here's a high point of the graph, right? Now, if there weren't arrows on this graph, we would also consider this point and then this point right here to be like high or low points of the graph of the function, right? So you'd of course like want to identify what the coordinates of all those points are, right? So like this is -4, -1, and this is -1, 2, etc. And that would like give you what those extra points are going to all be, right? And then for this graph of the function, the coordinates are already labeled, right? So those are going to be extrema points. Now, if we do assume that this right here is an arrow and this right here is an arrow, because the graph keeps going up and up and up and up and up, and then down and down and down and down, like there's no maximum point that's going to happen right there. And then similarly right here, there's no minimum point that's going to happen right there. So the only maximum points that we're going to be able to find on that graph is just those 4 points that I've labeled already. Okay, so let me actually take the time now and talk about what it means for an extrema point, or just extremum to be a relative extrema or absolute extremum, right? So a relative extremum just means that it needs to be a max or a min that is the highest or the lowest, respectively, in some open interval of the domain of that graph. So basically what that means is just in that particular little area of the graph, not the entire graph, it's just a high point in that particular area. Okay, versus an absolute extremum, the absolute extremum needs to be the highest y value overall or the lowest y value if we're talking about a minimum. So it needs to be a max or a min that is the highest or the lowest in the entire domain of the function. Okay, so rather than just some open interval of the function, it needs to be in the entire domain and be the highest and the lowest. Okay, so jumping back, sorry, we need to go backwards here to those couple of graphs that we saw. When we look at this first graph that we see right here, all 5 of these orange dots are all going to be relative extrema. So yeah, all 5 are relative, either maxima or minima, right? So this point right here would be considered a maximum. This point right here would be considered a max. This would be a min. This would be a max. And this right here would be a min, right? And they're all relative. So if we were to identify the absolute, this right here is the absolute lowest. So that would be the absolute minimum. And then this right here is the absolute maximum. Okay, and then the other 3 points, they can't be the absolute because they're not the highest and the lowest. Okay, and then in this graph right here, there actually is no highest or lowest point because, like, right here, obviously this point right here is higher than all the other orange points, but because the graph keeps going up and up and up, there is no absolute highest and there is no absolute lowest. So this graph right here has no absolute extrema at all. Okay, because there is no highest and no lowest point. So those 4 orange dots are relative extrema, but they're relative extrema only because they are not absolute. We're going to look at a couple of examples of being able to model some different scenarios and work with these couple of problems. So in this very first example right here, we have 2 individuals, Hector and Kendall, that are both leaving from the same town, Sioux Falls, South Dakota, at the same time. Hector drives south at a rate of 75 miles per hour, while Kendall drives eastward at a rate of 70 miles per hour. So there's some different parts right here, so let's just focus on one of the parts to begin with right here, and that would be this part right here, which is to express the distance between the cars as a function of time. So what we want to do right there is really write some sort of relationship in which the distance is the output and the time is going to be the input, since we want it to be a function of time, right? So it would be really helpful to draw a picture of what's happening right here. So we know that if we say that, like, right here, this is where Sioux Falls, South Dakota is located, right? We have one of our individuals, Hector, that's driving south. So this direction right here is where Hector is headed, and we also know that he is headed at a rate of 75 miles per hour. And then Kendall is headed in an eastward direction, which would be this direction right here at a 90-degree angle to south, of course, at a rate of 70 miles per hour, right? Okay, so what we want to do is we want to express the distance between the 2 cars. So if Kendall's car was located right here and Hector's car was located right here, the distance between those couple of cars would be this diagonal distance between them, and that's that distance that we want to represent as a function of time. Okay, so because south and east make a 90-degree angle with one another, we ultimately have like a right triangle relationship happening right here. So that distance should really be if we were to square the distance, the sum of the squares of the distances of the sides of that right triangle, right? So we can just really use the Pythagorean theorem, a squared plus b squared equals c squared, to represent this, right? So this distance that we're seeing right here is really coming from distance equals rate times time, which would be 70 times the number of hours, or the amount of time that Kendall would be traveling. So that's really her distance right there. And then Hector's distance would be 75 times t equals his distance, right? So ultimately, if we just took the quantity of 75t all squared, and then plus 70t all squared, that should equal the distance between those two cars squared. And then if we want to get just that d alone, we could square root both sides. So the square root of 75t squared, so it would probably be advantageous for us to actually square those couple of numbers. So if you squared 75, you're going to get 5,625 t squared, and then plus 70 t squared, which would be 4,900 t squared. That should be just equal to the distance. And then because those are like terms, the 5,625 and 4,900, we can combine those like terms and just come up with a little simpler of an equation right here, where distance as a function of time is just going to be the square root of 10,525 t squared right there. So that really addresses this first question right here in terms of coming up with a function, right? So then in the second question right there, we're asked to find the domain of the function. So domain just means like, what are the inputs, all of the inputs that can go into this function, right? So in thinking about that, you have to understand that time is the input in this function, right? So it should be hopefully clear that we don't want to put in negative amounts of time because, you know, we're not going backwards in time right here. So basically, right, we just really want time to be either 0 itself or greater, right? So that's pretty much it, just in terms of identifying the domain of the function. So I'll highlight that for the answer of that. And then the last question that we're asked about right here is to find what is the distance between the two cars after 2 hours of traveling, right? Well, since we have our function rule, we should be able to figure out that out just by plugging in 2, of course, right? So the distance between those two cars, or this diagonal distance right here, after 2 hours, would just be the square root of 10,525 times 2 squared, or just times by 4. So you'd be square rooting this number right here, 42,100. And then when you put that in a calculator, it comes out to be, if you approximate, about 205.18. And this is going to be in miles for distance then. So that would be it right there for the distance between those two cars after 2 hours. In this application, we have that a farmer wants to build a rectangular fence using an existing side of his barn to be able to bound one side of this. We know that he has 84 yards of fencing in which to be available to construct this fence. So in the very first part right here, we want to be able to write a function. And it says that we want to express the area of the fenced-in area here as a function of the length of one of the rectangle sides. So we need to input the length of one of the rectangle sides into this, and then spit out the area of this fenced-in area, right? So let's get a little picture of what's happening right here. So we know we want to have a fenced-in area that's supposed to be the shape of a rectangle, and then we also know that we only need to put fencing up on 3 of the sides of this rectangle because the barn is going to bound one of the sides. So we'll just assume then, how about this side right here? Be the side that the barn is on, so we only need fencing on those other 3 sides, right? So if we want to input just one length of this, of the rectangle right here, just one of the lengths, then we might just denote that maybe that length right there has length x yards, which of course means then the side across from it would also be x. And then that third side that we need to put fencing on is not going to be necessarily the same as x, right? So if we know that there's 84 total feet of fencing available, we would just need to take that 84 total feet and subtract 2x, how much fence was put up on those other sides, and that would be how much fencing we're going to put up on that third side, of course, right? So now what we want to try to do is we want to try to write an area function as a function of the length of one of the rectangle sides. So since we're dealing with a rectangle, area of a rectangle is length times width, right? So area equals length times width. But then we know that the dimensions corresponding to the length and width here are x for width, let's say, and then 84 minus 2x for length. So we could substitute in 84 minus 2x for length and x for width, and then we can simplify that if we so desired and get negative 2x squared plus 84x is equal to area as a function of x. And that would give us that function that we desire. We're inputting one of the lengths of the sides of this rectangle in for x, and then getting the area of that rectangle as an output, right? And then in part B, we're asked to find the domain of the function, which is to specify the set of all of the inputs that can go into this function, of course, right? So x, in this case, is really just the length of a side. And so we know that distance always needs to be positive, right? So we would desire for x to basically be above 0. I probably wouldn't put equal to 0 because we need the rectangle to actually have some area, right? So be above 0 at least. But then also, furthermore, not only that, but we do need this side right here to also be positive. So we also desire for 84 minus 2x to be greater than 0. And then if you solve that second inequality just a little bit to isolate the x, so by first of all subtracting 84 from both sides, and then if you divide by negative 2, that's going to flip the inequality because you divided by a negative. That would be not 84, 42. So if we integrate those couple of things together with each other, these couple of inequalities, saying that x has to be greater than 0, but then also x has to be less than 42, then we would know that our domain for this function is that x has to be between 0 and 42, then exclusive. So excluding 0 and excluding 42 from possible values of x in the domain. That ensures then that the length and width are actually going to have, positive measures. And then the last part of this right here is asking us to find the dimensions that maximize the area of this fenced-in area. So figure out what's going to give us the most possible amount of, green space to put in this fence. So if we look at the function that we're using right here, this function is a quadratic function because we can see that the highest exponent on x is a 2. And so we get a parabola. And then furthermore, because the coefficient of that x squared term is negative, for negative 2, we know this parabola opens upside down. So we would be able to maximize the area at the vertex of that parabola, so at the highest point. So we could easily identify that point if we were to graph this function. And I've already done that, as you can see right here. And so if you were to just find the coordinates either on a graphing calculator, of course, 2 or Desmos or whatever graphing tool that you have available, you could state then that the coordinates there are at 21 for x and 882 for y. So in particular, when x is equal to 21, so if this was 21, this was 21, and then this was 84 minus 2 times 21, which would equal 42. So dimensions of 21 by 42, that actually equals an area of 882. That would give you, the fenced-in area that would have maximum area. So the question specifically asks, I think, for the dimensions, right? To maximize the area. So you would want it to be 21 yards by 42 yards to maximize the area, but then also like the maximum area would be 882 square yards as well. Here we want to look at the graphs and equations and values of functions related to piecewise functions. So we're going to look at a contextual example to begin with right here. So just very recently, as of January 2024, the cost of being able to mail a flat through the United States Postal Service was $1.39, but that's for a weight that's not over 1 ounce. As it gets heavier, for each additional ounce above 1 ounce, there's an additional 24 cents that they're going to tack onto that charge. So representing this in just sort of a table, ultimately the earliest cost that you can have is $1.39, but that's for the weight that's not over an ounce. So if the weight is less than 1 ounce and then also equal to 1 ounce, then it's going to cost that, right? Now, to also get a little bit more specific with this, the weight's not going to be negative, and also the weight's not going to be zero because then you're not mailing something. So if it's just strictly above zero, right? That would cost $1.39. So then it would cost an additional 24 cents, so bring it up to $1.50 or $1.63. If it weighed up to 2 ounces, so if the weight was equal to 2 ounces but under, then I have to stay above one, right? Because we went below one, and then it cost the $1.39. So between one and two, excluding the one, including the two, right? It's going to cost $1.63. So if you just kept going by adding 24 cents, and now you went to $1.87, and that would be for weights that are between 2 and 3 like this, excluding 2, including 3. And then for this, add another 24 cents, it's going to cost you $2.11, etc. Right? So you get the idea of how this would pan out. So let's look at this graphically. So graphically, what's going to happen is we might want to put the weight in ounces on the x-axis, because that's really like the input, right? And then put the cost in dollars up there on the y-axis. So weight-wise, we could maybe say like this is 1 ounce, this is 2 ounces, this is 3 ounces, 4 ounces, 5 ounces, etc. And then cost-wise, we could maybe count by 25-cent increments. This would be like $1 maybe. Straight here would be $2. Up here would be $3, etc. Right. So what should happen then is for this interval of the domain between 0 to 1 ounces, it should cost $1.39, right? So what should happen then is right about here, just have like a flat little horizontal line, because every package, no matter how much it weighs between 0 and 1, is just going to cost $1.39. We'd specifically need to put a little open circle right here, and then a filled-in circle right here, to designate that at 0, it's not actually going to cost anything right there. And then at 1, it's going to cost $1.39, right? So then between 1 and 2, it's going to cost $1.63. So like right here, we'd have another little interval like that for $1.63. And then at $1.87, so like right there, that'd be between 2 and 3. And then for $2.11, right above there, it's between 3 and 4, etc. Right? So what we get is what we call a piecewise function. So this is just basically a function that's in different pieces, just based on the different intervals of the domain of the function, right? So what you should see happening right here is like you have kind of this portion of the graph and then this portion of the graph, different intervals of the domain of this function upon which the pieces are defined, right? And that's what we're going to see happen in different piecewise functions. So what you see right here just graphically are examples of piecewise functions. So this first graph right here, you can see that, it's split up into different pieces. But sometimes the pieces in which you split up the intervals of the domain, right? So you have this interval of the domain between 5 and 10, right? And then this interval of the domain between like 5 and 3. Cool, you have the different pieces, but they can sometimes like connect and touch each other, right? But there's no like one single equation that's defining the entire thing, right? You can have separate little equations for each little part of the domain, right? So what that looks like in terms of actually defining a single equation for the different pieces, it looks like something that you're seeing right here for this function k of x. So the function k of x is a function. It's just all of these things right here are really the different domain restrictions. So it's saying that, for example, when x is less than or equal to -2, okay, then you're going to use this rule to map to your y values. But then when x is between -2 and 0, then you would use this rule to map to your y values, right? So you're not using all of the different rules for every single x value. You can only use, one rule given the specific domain restrictions that we have. right? So what we're asked to do right here is we're asked to use the piecewise function k of x to find each of the following, right? So if we were to ask to find k of -3, we would need to know what rule we should use based on what part of the domain -3 is in. So of all these domain restrictions, this right here is where -3 is going to be because -3 is less than -2. So the rule that we'd want to use is negative of x cubed plus x squared. And then plug in that -3, okay? So you would get negative of whatever -3 cubed is, which is going to be -27, and then plus the square of -3 is 9, so it ends up being 27 plus 9. So right there we get an answer of 36, and 36 only. So that's the only thing that we would plug into. We're not plugging into all of the different rules. Right here, we're asked to find k of 0. So that's actually going to land right here. So you just have to be careful about that because it's not going to be right there because 0 is not included right there because of this just strict less than, right? So it has to be in the what you're seeing right there. So the rule we'd want to use then is that rule that is the quantity of x minus 2 all squared, and then we can plug in the 0, right? Then if you just follow PEMDAS, you get -2 in the parentheses, and when you square that, you get an answer there of 4, right? And then you'll see that, like, define k of 5. Okay, so right there, between 3 and 7 is where 5 is going to be. So the rule we're going to use right there is 8. Oh, well, 8's just a number. There's not actually an x to plug into. So the answer right there is just 8. Okay, so if you're plugging any number between, like, 3 and 7, right, the answer is always going to be 8. And then for this number right here, that's -3/2, which is -1.5, right? -1.5, that's between -2 and 0. So the rule that you'd want to use then is that absolute value rule. So -2 times the absolute value of x minus 3, and then plug in that -3/2, or -1.5, right? So following PEMDAS, inside of the grouping symbols absolute value, you need to subtract those couple of numbers. So -1.5 minus 3, that would give you -4.5. And then next what you need to do following ordinal operations is just absolute value that number. So it becomes a positive 4.5. And then you'll be able to multiply that positive 4.5 by the number in front of it, which is -2. And then it becomes -9 for the y value or the output value there. And the last thing that we have right there is to find k of 10. And nowhere in the domain right here is 10 actually included. Because right there, x is supposed to be just strictly under 10. Nowhere does it say that x is equal to 10. So like x equals 10 is not in the domain of this function k. So if it's not in the domain of k, we don't know where to send 10 then, right? So if we're going to find k of 10, it'd be impossible to find 10, right? So k of 10 just, it doesn't exist. There's no function value that exists for 10 under the function k in this case, right? All right, let's take a look at an example now where we can actually do some graphing of the function. So here we're asked to graph the function f of x. Now, f of x kind of has two different pieces to it right here, right? So one piece of it is going to be this piece right here. All that that's saying right there is just y is going to equal 2x plus 2, okay? That's just a line, mx plus b. But what needs to happen right there is it can only equal 2x plus 2 only specifically when x is less than or equal to 4, okay? So how I would go about this is I would just graph that as you know how to graph that. Just graph y equals 2x plus 2. So of course that means that you would have a y-intercept at 2, and then because the slope is 2, you'd go up 2 over 1. Of course, like, you'd want to make that continuous and connect it to graph your line, right? Now we just keep in mind though that we only want this graph when x is less than or equal to 4 for our domain. So here is where 4 is. So really we only want on this part of the domain the graph of 2x plus 2. So we really only want then from this point, because that's corresponding to x equals 4, and then to the left forever, that graph. So like up here where the line would continue, we don't want that because we want it only on the domain when x is less than or equal to 4, right? And then the other thing that we have going on right here is that we have that y should equal negative x, but specifically only when x is strictly above 4. So really only on this part of the domain, right? So put that little empty circle at 4 because we don't want anything happening at 4 for when y is equals to negative x, right? So I would, again, just graph y equals negative x. Normally, like you know how to do, this is also going to be a line, of course, right? But it's just going to start at the origin because it'll be its y-intercept, and then it has a -1 slope, so it should go like this, right? Now, the thing is that we only want it in this part of the domain of our function, so really it should start like right here, basically, and then go forever this way. So we only want this piece right there. So all this other, these dots, we can erase it. We don't need it, and I don't even need to show what that is, right? Yeah, so you definitely want the arrow because it's going to go on forever. And then the other thing that would be really critical here is that at 4 itself, you need to have an open circle right there, because 4 is not in the domain for that piece right there. So what you see as a full entire graph right there is the graph of this particular piecewise function, right? And then just for another example right here, being able to graph a piecewise function, you should ultimately just be able to see that, okay, so only in this interval of the domain. So just between -6 to -1, right? So just in this portion of the graph, should you graph whatever the rule is in this case, right? And the rule that we see right here is equal to -2. So if you're to graph y equals -2, that's just a horizontal line. So you would have really just that right there, between -6 to -1, okay? And then pay attention to what sort of inequality symbols you have right there. So because those inequality symbols both have equals to underneath them, you need to make sure you designate open circles, or filled in circles, because we want to include -1 and -6 as part of the domain right there, right? So that's what you want that piece to look like. And then for the next little part right here, we've got the domain is going to be between -1 to 3. So we're really looking at this little portion of the graph, right? And in that portion of the graph, what we want is we want the equation y equals 1 minus x squared, right? So you can make a table of values if need be, but ultimately this should just be a parabola that is shifted up 1 and then also should be upside down, right? So it's going to look something like this because you have it shifted up 1 and then it's going to go upside down. So like 1 squared, 2 squared, 3 squared down from where that vertex was, and then also right here. But then that'd be pretty much all that you would want. You wouldn't want to continue the parabola anymore because it needs to stay between -1 and 3 in terms of the domain, right? So just make sure that at this particular point right here, there's going to be an open circle because -1 is excluded from the domain right there because of that strict less than. And you'll continue the parabola all the way until you get to right there, and then have it that filled in circle because 3 is in the domain for that particular piece of this function, right? And then the only other thing that you need here is you just need y equals 3/4 x minus 5. And that's specifically when x is, there's a typo in my part right here. So this right here is supposed to be a greater than symbol, so just change it to that. So at -5 is where this would start, right? And then it's supposed to go at a slope of up 3 over 4, up 3 over 4. So if we were to graph this line, it would look something like this. However, we're supposed to only graph this line on the domain where x is greater than 3, so everywhere over here. So you just kind of need to snip the graph off right there where it kind of hits 3. So like right there is where it hits 3. So the graph is really only going to start where that purple dot is, right? And then just go at that slope of 3/4. So I'm going to hit here and then up 3 over 4, sort of deal like that. And then actually at that particular point where I started it, it needs to be a open circle because it's strictly greater than 3 based on what I corrected it to there, of course, right? And then this right here just kind of has a special case of what could happen with a particular equation, and specifically just this first part that you're seeing right here. So if we were to graph y equals x squared minus 9 over x plus 3, you could make a table of values, but you should notice, like, there's an x squared minus 9 at the top right there, which factors is x plus 3 over x minus 3, and then the bottom of that is x plus 3, and then you'll be able to cancel out the factors x plus 3 and just get the equation x minus 3. So that just says that y equals x minus 3, right? Now, this is only going to happen when x is not equal to negative 3. So for the entire real numbers then, just at negative 3 itself, we don't have a function value. So if you're going to graph y equals x minus 3, that's just a line that should start at negative 3 for the y-intercept and then have a slope of 1, right? So you really just want to graph this line, okay? But at negative 3 itself, right, 4x, we don't want anything right there. So as soon as I get to like right there, so right here, there should be a little hole, okay? So really, I want this entire just red line that I've drawn, okay, to go on forever and ever and ever, but at x equals negative 3, there's going to be that little, there's a hole right there, right? So that's empty. It's not a filled-in hole. It's an open hole graph right there. And then the only other thing that we have is that when x equals negative 3 specifically, so only at x equals negative 3, should we have a y value of 4. So there should be like a singular point, that at negative 3, I'll just have a single point right there. So that's it. That's the graph of that piecewise function, right? All right, and then we can skip over these couple of things right here, and then jump to the very last part of this, in which we're asked to write an equation for this piecewise function that we're seeing right here. So to be able to write an equation for this piecewise function, you should recognize that there's like, what, 4 pieces to this. So let's talk about that piece right there. That's ultimately just the equation y equals 6, right? And then you just have to recognize like what domain that's on. And that's y equals 6 only when specifically x is strictly below negative 4 and forever, right? And it's strictly below because you see there's that little empty circle right there. So that's what you have right there, okay? And then you can also see that you've got this little piece right here. That's a line, so you can hopefully write that in like mx plus b form, right? And you can actually see that the y-intercept of that is negative 1, and then the slope of it seems to go up 2 and over 1, up 2 over 1, so you also know that the slope is equal to 2, so that's really just y equals 2x minus 1, okay? But the graph is really only between these particular x numbers of negative 4 to 0, so it's only when x is between 0 and negative 4, and then because that piece does have filled in circles, you can put equal to's underneath those less than symbols, right? And then you've got this little parabola, right? And it's really just a parabola that's like shifted down to negative 4, because that seems to be where the vertex is, right? Because it's going up 1 and then up, yeah, 4 right there, and then up 9 right there. So yeah, that's just going to be y equals x squared minus 4 right there. And then it's specifically happening when x is between just those couple numbers, 0 and 3. So not including 0, because you got that little empty circle. But then we could say, I guess we could argue for when it's equal to 3. Okay. And then the last part of this right here, this little piece right there, which is also a line, right? Now, if we're going to write a line, we would hope that we could get an mx plus b for that, but we don't know exactly where the y-intercept is. So maybe if we were to find the slope of this, so it looks like it's going through this point right here, and then that point right there, so it's going over like 4 right here and up 5 right there. Then it seems like we've got a slope that's equal to, write it over here, a slope that's equal to negative 5/4, right? So if we kept going up 5 and then over 4, it looks like we're going to have like a decimal y-intercept, right? So what we could do is we could maybe write this in point slope form to find and solve for the exact y-intercept. So since we know the slope is -5/4, and then we could use like maybe this point that's on the graph of 7, 0. Then if we put this in point slope form, y minus 0 equals -5/4 x minus 7. And then we could use the distributive property and get -5/4 x plus 35/4. That would be the equation for that thing, right? And then we can also acknowledge the fact that this is happening when x is between like 9 at the highest right there. It's got the little empty circle, so just strictly less than 9. And then when it's higher than 3. So I just want to make sure that like right there, what I just circled in black, and then right there, what I just circled in black, that those couple of inequalities, one of them has an equal to, but the other one doesn't, because I don't want to have the input of 3 going to 2 different rules at the same time. Okay. All right, so now we need to actually write the piecewise function. So maybe this function has a function named f, right? So I want to say that f of x is going to equal, and then have all of these 4 different separate rules. So what you'll need is you'll need a brace, a left brace, and a left brace only. You don't want a right brace. And then you can say that it equals all these different rules. So it equals 6, and then you put a comma, and then specify the domain on which it equals 6. And so we said that it was supposed to be when x is just strictly less than -4. And then also it could equal 2x minus 1, and then you can put a comma, and that was when -4 was less than or equal to x, and then also less than or equal to 0, right? And then it also equals x squared minus 4, and that was specifically when 0 was strictly less than x, which was, we said less than or equal to 3. And then finally, when we have -5/4 x plus 35/4, and then when x, which is also less than 9. So this is what we would want right there to be able to write the equation for that piecewise function.